Hi everyone. The last lecture of this course is going to talk about type soundness and research conducted at the Programming Language Research Group at KAIST. We are going to discuss type soundness briefly and take a short break, and then I'm going to introduce what kind of research is going on in our group as a follow-up work of this course material. Type soundness. Type soundness is a theorem of the form this. If the type of this expression is tau under no assumption, then running that expression never produces an error. Meaning that when the type checker says, oh yeah, it does not have any type error, and when you evaluate this expression, its resulting value is going to have type tau, then actually running this expression will not go bad. Okay, that's type soundness. This is really important. This is a really important theorem, and you may get questions about this in some exams like graduate school entrance exam or some industrial entry-level questions and things like that. One more time, type soundness is a theorem saying that when the type checker says okay, executing it has no problem. However, if we add division to the language, until now we had plus and minus, sometimes multiplication, but what about division? It's weird because divide by 0 is going to be an error. It's a division by 0 error, maybe okay, right? Because that's the semantics of division. So we do like to say that if type checker says okay, then running that expression never produces an error except divide by 0. Or one may claim that divide by 0 is not an error, is an exception, an intended behavior, right? So it's kind of a philosophical question. Is it an error or not? In general, soundness rules out a certain class of runtime errors, meaning that when we say it's sound, then it's gonna reject runtime errors, not all of them, but some class of runtime errors like type errors, right? So when we say, soundness failed, then that means that even though type checker said okay, there is an error at runtime. Then where is the problem? The typing rules may have a problem. Let's see an example. As I mentioned before, we have a problem with TVFAE. TVFAE has a bug in its typing rule for with type definition. Why? What happens? Let's look at this concrete example. We are defining a new type named foo, which has two variants A and B, and their fields have the same type num and num. Okay, so far so good. Foo has two variants A and B, and their fields have type num. Now that we define this type foo, let's use it. I'm defining a function which takes a parameter whose type is foo. Yeah, just the type foo that I defined. And in the function body, we say, hey, you x, you have type foo, so I know it's going to be either A or B. And I also know that both A and B have one field of type num. So when A has a field and B has a field, they both have num type, so I can add 3 or 4 to them. So far, so good, no problem. So when we interpret this expression, we are gonna result in closure V of parameter type foo, and the body expression is like that. What's the argument expression? In the argument expression, we're defining another type foo, the same name. And it has two variants, A and B. Ooh. But the thing is, while B has a field of type num just like this foo, but this foo's A has a field of type boolean. Ooh, it doesn't smell good, right? Something is gonna go bad. How? Look at that. You know this function part? I said it's gonna result in a closure V whose type is gonna be foo arrow what? The result type is gonna be the type of these expressions, which is num. Okay, and what's the type of this expression? We are defined this new type, and A has a field of type boolean, so the type of this one is foo. Okay, so what we expect is that this one has type foo arrow num. This one has type foo. So when we have functional application to this, we expect to have num. There's no type error. Yeah, happy. Let's run it. When we evaluate this argument expression, we are gonna have A true. When we apply this value to the function, this one, we are gonna pass this to X, and X's type is foo. Looks like okay, but really. And then we say, hey you, A, are you A or B? Oh, I'm A of true. You're A of N. True is gonna be bound to N. N's value is true, and we are adding true to 3. Runtime error, runtime error. What's going on? Even though the type checker said, okay, this type is this one, the second expression's type is foo, so functional application is type num, there's no type error, it's good to go, run it. And we trusted the type system and ran it, and we got a runtime error. That's bad. We don't want to have that. That's why we had the compile time type system. What's wrong with that? Because there was a problem in the typing rule. I'm going to show that in a minute. So the solution could be, the problem is, the type of this one is foo, arrow, num. And type of this one is foo, but what? 갸가 아니에요. This foo and that foo are two different foos. They are different. So one possible solution is to prohibit to having local type declaration. The issue is that we have one foo and the other foo. They are locally defined like that, and we are mixing them. So that's the problem. No local type declarations. You can define types only in the global level. That's one option. The other option is to prohibit using T beside its scope. Don't let T escape its type definition. Let's look at this example again. This type foo is locally defined from here to here. This foo is locally defined from here to there. So this foo and this foo are two different foos, and they should not overlap. When we say foo here, that should be this, not this one. So that's the point. Look at this typing rule again. Remember, under a given type environment, when we have this expression, what's the type? We have to extend this given gamma to gamma prime by adding 3 pieces of information for the name T and the name of the first variant and the name of the second variant. Using that extended type environment gamma prime, we checked the wherefromeness of the type of the field of the first variant. We checked the wherefromeness of the type of the field of the second variant. And finally, we check the type of this expression under the same gamma prime, and the type of that expression was the type of the whole expression. That was the old broken typing rule. Why is it broken? Because the locally defined type T, which is extended into gamma prime, that's gonna be used in type checking this expression E, meaning that the T may be included in type tau 0, meaning that the T may be in this tau 0. It's escaping. 도망간다. 그죠? It's escaping its scope from here to there. So we need to prohibit this. How can you prohibit that? We first need to say that, hey, you, new type T. This should be new, meaning that under this given gamma, we should not have the same name T. So that's the first thing. And then when we check the validity of this resulting type tau, we are not going to use gamma prime. We are going to use gamma, meaning that tau 0 should be okay under this given gamma without using T. That's the fix. Is it clear? Yeah. So this is just one simple example showing that typing rules may have a problem. You know what? Java type system once had a soundness error. Rust type system has that. Scala used to have one. Many advanced programming languages even used to have type soundness problems. Meaning that even though type checker said, okay, you can run this code without any problem, at runtime, you got a problem. In such cases, we need to go back to the type checker and identify the problem and fix it. That's type soundness. Again, type soundness is really important. It's a theorem saying that when an expression is well-timed, then running that expression never produces an error. This is a very important theorem, and when a language is proved to be type sound, when we prove this theorem for a given language, then when the program in that language is well-timed, running that expression should not throw an error.